Hello everyone, I welcome you all for first lecture on partial differential equations. In this lecture, I will discuss three topics. What is partial differential equation, formulation of partial differential equations, and numerical problems. We already know about differential equations. An equation containing differentials or derivatives is called a differential equation. This is partial differential equation. Partial differential equation is a differential equation which contains partial derivatives. These equations arise in geometry and physics when the number of independent variables is 2 or more. For example, we want to study what is the temperature at any point in a solid or at any place. Then the temperature may vary from point to point in a solid as well as from time to time. So as a result, we can say that temperature theta is a function of position, that is x, y and z coordinates, and fourth variable will be time. So we can say that f is a function of x, y, z and t. And as we change these variables x, y, z and t, temperature will change. It may be constant also, but we can say that these derivatives, partial derivative of temperature with respect to x, or derivative with respect to y, or partial derivative with respect to z or t, will be non-zero. We can talk about higher order derivatives like second order partial derivative of theta with respect to x, and this is the notation del square theta divided by del x square. Then we can talk about mixed derivatives like the second one, del square theta divided by del x and del t. Next one is last term, that is third order derivative of theta, where we are differentiating with respect to x twice and with respect to t only once. So this is the definition of partial differential equation. An equation relating partial derivatives is called a partial differential equation. For example, del square theta divided by del x square, this is equal to del theta over del t. This is second order partial differential equation. The order of a differential equation is the order of the highest derivative appearing in the differential equation. So in the first equation, on left hand side we have second order derivative, and on the right hand side we have first order derivative. So we will say this is a partial differential equation with second order, right? Next one is del theta over del x raised to power 3 plus del theta over del t, this is equal to 0. So this is first order partial differential equation where I am taking theta as a function of x and t. Similarly, we can have third equation, right? So this one is second order, please correct it, this is second order partial differential equation. So in this lecture we will discuss first order partial differential equations, where I will take z as a function of two independent variables x and y. These are some standard notations. Partial derivative of z with respect to x is denoted by small p. Derivative of z with respect to y, first order, is denoted by q. And r is the second order partial derivative of z with respect to x. Small s is the second order partial derivative of z with respect to y, and t is second order derivative of z with respect to x once and then with respect to y. So all the notations given by 1, these are standard notations, right? So we can say that any first order partial differential equation can have terms like x, y, Z, P and Q. For partial differential equation, we will discuss two things. First, formulation of partial differential equation, and second is solution of a partial differential equation. First, we will discuss formulation of a partial differential equation. There are two techniques. First, elimination of arbitrary constants, and second is elimination of arbitrary function. Solution of a partial differential equation, we can talk about general solution or particular solution of a partial differential equation. Now I will discuss some examples. Equation of some surfaces, some specific or in general. Consider example 1. X square plus y square plus z minus c whole square equal to a square. It represents the set of all spheres with centers on z-axis and radius is a. Here a and c are arbitrary constants. As we change a, size of the sphere will change, and as we change c, then the center of the sphere will change. So we will discuss partial differential equation representing this family of surfaces. Now consider example 2, z equal to f of x square plus y square, where this f is any arbitrary function, right? So it represents the set of all surfaces which are symmetrical about z-axis. Because in this one, x and y, they are appearing in the form of x square plus y square. You take point in first quadrant, second quadrant, third quadrant or fourth. Then the value of this expression x square plus y square is always 1. So we have the same value of z coordinate corresponding to any point xy, or you take some other point. For example, you can take 1 1, minus 1 minus 1, 1 minus 1, or other way also. So this f is any arbitrary function. You change f, then correspondingly you have a new surface, but that surface is always symmetrical about z-axis. Now consider example number 3, x square plus y square equal to z minus c whole square tan alpha square. It represents the set of all right circular cones whose axis coincides with z-axis. Here alpha and c are arbitrary constant. As you change c, the vertex of the cone will change. Alpha is the inclination of that line. So you change alpha, you change c, you will get different cones. But all these cones, they are symmetrical about z-axis. Now I am taking example number 2 again, and we will try to see how this function z equal to f of x square plus y square is representing surfaces which are symmetrical about z-axis. Let f of t be t, just t function. Then we put t equal to x square plus y square. Then this function will be z equal to x square plus y square. And we know that this is a paraboloid, and clearly see the graph on the left hand side, it is a paraboloid. If I take f of t equal to square root of t, then what will be z? This function star will be z equal to under root of x square plus y square, and in this it is going to be cone. You can see on the right hand side, right, its vertex is 0 0 0, and this is the graph of your function, right? So we can say that this star, depending upon how we are defining this function f, whatever is the formula of that function f, for example I took t, then I took root t, then x and y, they are always appearing in the form of x square plus y square. So whatever is this surface, it is always symmetrical about z-axis. Now I will explain origin of first order partial differential equation. For this one, we pick three surfaces as discussed earlier. Sphere with center on z-axis, right? Second one, I will pick equation of the cone, and third one, I will pick the arbitrary function z equal to f of x square plus y square, right? So start with the first one, equation number 1, x square plus y square plus z minus c whole square equal to a square. A and c are arbitrary constants. So this equation 1 represents the set of all spheres whose centers lie along the z-axis, right? So there are two arbitrary constants, and I am assuming that z is a function of two independent variables, x and y, right? When no information is given, we always treat z as dependent variable, x and y as independent one. So start with equation number 1, differentiate both sides with respect to x. We treat y as constant, so the derivative will be 2x plus 2 times z minus c curly z over curly x. This is equal to 0 because derivative of y with respect to x is 0. Now derivative of z with respect to x I have underlined. This is p. So we have finally equation number 2. Now again start with equation number 1. Differentiate with respect to y. We have 2x plus 2z minus c curly z over curly y. This is equal to 0. Divide by 2. We have equation number 3. Now you have equation number 2, equation number 3 and equation number 1 also. So using these three equations, you have to eliminate these two arbitrary constants a and c. You can use these equations the way you want, right? So just see equation number 2 and equation number 3. We have z minus c is common. So we can eliminate z minus c from these two equations 2 and 3, and finally we have equation number 4. You can simplify this. So finally we have py minus qx equal to 0. So this equation number 4 characterized the set of all spheres with centers on the z-axis. Now consider next example given by equation number 5, where alpha and c are arbitrary constant. This equation represents the set of all right circular cones whose axis coincides with z-axis, right? Now differentiate equation number 5 with respect to x. We get 2x equal to 2 times z minus c tan alpha square p, where this p is the derivative of z with respect to x. So we have equation number 6. Now again differentiate equation number 5 with respect to y. We have 2y equal to 2 times z minus c tan alpha whole square q, that is equation number 7. Here q is derivative of z with respect to y. Now using equation number 6 and 7 only, we can eliminate c as well as tan alpha. You can divide these two equations, left hand side and right hand side respectively, and finally we have equation number 8, py minus qx equal to 0. If you recall equation number 4 on the previous slide and this equation number 8, both are same, but we are getting these equations, one from the sphere and other from the cone. Their geometrical shapes are totally different. It means there is something common between cone and sphere, because we are getting same partial differential equation for this one. So I will discuss what is the common thing between cone and sphere after the next example. So as discussed, for the sphere and the cone, we have the same partial differential equation, and I asked what is common between these spheres and these cones. If you see graphically, both the spheres and cones, they are surfaces of a revolution which have z-axis as axis of symmetry. The cone is also symmetrical about z-axis, and the sphere is also symmetrical about z-axis. Now the next example. All the surfaces of revolution with this property that they are symmetrical about z-axis, they are characterized by an equation of the form 9 z equal to f of x square plus y square, where this f is an arbitrary function. Alright, so in this one we have just one arbitrary function. We try to eliminate this arbitrary function f and find the partial differential equation for the surface given by 9. Now differentiate 9 with respect to x and y. For this one we will use chain rule, or you can just simply differentiate it. Let us define u as x square plus y square, argument of the function in equation number 9. So I can rewrite equation number 9 as z equal to f of u. Now we have z is a function of u and u is for the function of x and y. Now z equal to f of u, start with this equation, differentiate both sides with respect to x. On left hand side we get derivative of z with respect to x. This is equal to f dash u, and partial derivative of u with respect to x. Now we know derivative of z with respect to x. This is equal to 2x because u is x square plus y square. So finally we have equation number 10, that p is equal to f dash u 2x. Now again start this equation, z equal to f of u, differentiate both sides with respect to y. We have derivative of z with respect to y is f dash u, derivative of u with respect to y, and derivative of u with respect to y is 2y. Finally we have equation number 11, q equal to f dash u 2y. Now from equation number 10 and 11 we have to eliminate function f, which is appearing in the form of f dash u. So you can eliminate it. So finally we have p by q, this is equal to x over y. Simplify this, we have equation number 12. So we can see from these three examples that the sphere with center on z-axis, then cone with axis along z-axis, and the surface z equal to f of x square plus y square, all are solutions of the partial differential equation py minus qx equal to 0. So we can say that first order partial differential equations tell us something about the symmetry of the surface. So they are telling about the geometry, the symmetry of the surface. Recall the results from ordinary differential equations. When we formulate ordinary differential equation for given equation, then the order of the differential equation is equal to the number of arbitrary constants appearing in the given equation. If there are two arbitrary constants, then their order of the differential equation is 2, and accordingly the relation is whatever is the number of arbitrary constants, same is the order of the ordinary differential equation. But in partial differential equation there is a change in this relation. It says that if the number of arbitrary constants in the equation of the surface is equal to the number of independent variables, then the order of partial differential equation is always 1. So I am repeating it again. Number of arbitrary constants is equal to the number of independent variables, then the order is 1. if the number of arbitrary constants is greater than the number of independent variables, then the order of the partial differential equation is greater than 1. What exactly will be the order? We can't comment about this, but yes, order is going to be greater than 1. So this is the second point. Now, if we are formulating partial differential equation by the second method, that is elimination of arbitrary function, then the order of the partial differential equation is equal to the number of arbitrary functions appearing in the equation of the surface. So these are three important points about the order of the partial differential equation for a given equation of the surface. Now the question is, why do we have this kind of relationship between the order of the differential equation and the number of arbitrary constants appearing in the equation of the surface? To understand this, consider z as a function of x and y. Here this function f is some known function, means relation is given with x, y and some arbitrary constants. So assume that there are two arbitrary constants, say a and b. Then we can start with the given equation of the surface. We differentiate with respect to x and y. Then we have two more equations. One equation containing partial derivative p and second one with partial derivative q. So now we have three equations given surface, equation containing p and equation containing q. And in these three equations, there are two unknowns a and b. So out of these three equations, you can pick any two equations, and using two equations, you can find out two arbitrary constants. You have a and b in terms of x, y, p or q. That depends on the equation. Now, third equation we have not used till now. So we just put the value of a and b in third unused equation. And finally, we can eliminate a and b. Similarly, for the second method, arbitrary function. Then you have z in terms of some function f. So if we take its derivative with respect to x and y, we will get f dash, or that depends on the number of arguments. So similarly, in that case, whatever is the number of arbitrary constants, same will be the order of the partial differential equation. We will discuss this in numerical problems, then it will be more clear for the second method. So finally, we have formulation of partial differential equations. First method, elimination of arbitrary constants. So let z be x plus y, y plus b, given by equation number 1. Here z is a function of x and y. Most of the time we take z as a function of x and y if it is not given in the question, right? Otherwise it will be mentioned if there are some other independent variables. So finally, in equation number 1, we have z as a function of x and y. There are two arbitrary constants, a and b, and number of independent variables is also 2. Both are equal. Number of arbitrary constants is 2, and same is the number of independent variables. So we have a partial differential equation of order 1. So start with equation number 1. Differentiate with respect to x. We get p, that is derivative of z with respect to x. This is equal to y plus b, equation number 2. Now again differentiate equation number 1 with respect to y. We get q equal to x plus a, that is equation number 3. Now equation number 2 and equation number 3. We can find out a and b from these two equations, and now substitute the values in equation number 1 and we get z equal to p q. So this one is the solution of this problem. Next problem, 2z equal to ax plus y whole square plus b given by equation number 4. There are two arbitrary constants a and b and z is function of x and y. So again, order of the partial differential equation will be 1 as number of arbitrary constants is equal to the number of the independent variables. So differentiate equation number 4 with respect to x. We have equation number 5, 2p equal to 2 times ax plus y into a. Differentiate equation number 4 with respect to y. Then we have 2q equal to 2 times ax plus y into 1, that is equation number 6. Now we have to eliminate a and b from these three equations, 4, 5 and 6. So just have a look. Equation number 5, we have p equal to a times ax plus y. And from equation number 6, we have q equal to ax plus y. So in equation number 5 and 6, we just have a. There is no b. So b is already eliminated. So we use equation number 5 and 6 and just eliminate a from this one. So I am calculating a from equation number 6. A is q minus y divided by x. Substitute the value of a in equation number 5. Simplify this. Finally, we have partial differential equation px equal to q times q minus y. There is no hard and fast rule that you follow in a numerical problem. Just looking at the problem, you can go accordingly and just eliminate the arbitrary constants. Now I will explain origin of first order partial differential equation. For this one, we pick three surfaces as discussed earlier. Sphere with center on z-axis, right? Second one, I will pick equation of the cone, and third one, I will pick the arbitrary function z equal to f of x square plus y square, right? So start with the first one, equation number 1, x square plus y square plus z minus c whole square equal to a square. A and c are arbitrary constants. So this equation 1 represents the set of all spheres whose centers lie along the z-axis, right? So there are two arbitrary constants and I am assuming that z is a function of two independent variables x and y, right? When no information is given, we always treat z as dependent variable, x and y as independent one. So start with equation number 1, differentiate both sides with respect to x. We treat y as constant, so the derivative will be 2x plus 2 times z minus c curly z over curly x. This is equal to 0 because derivative of y with respect to x is 0. Now derivative of z with respect to x I have underlined. This is p. So we have finally equation number 2. Now this is second method for the formulation of partial differential equations, elimination of arbitrary function. Consider problem given in 1, z equal to xy plus f of x square plus y square. Here f is an arbitrary function and z is function of two independent variables x and y. As there is only one arbitrary function, so the order of the partial differential equation will be 1. You can directly start with equation number 1 and differentiate with respect to x and y. Or you can just define a new variable u, which is equal to x square plus y square. It will be easy to take the derivative using chain rule. So after substitution, u equal to x square plus y square, we have equation number 2. I am just rewriting equation number 1. Z equal to xy plus f of u. You can see the diagram on the right hand side. F is a function of u and u is for the function of x and y. Right? We can add x and y at first level also. So start with equation number 2. Differentiate with respect to x on both sides. So on left we have p. This is equal to y plus f dash u, derivative of u with respect to x. Now use the function u, then derivative of u with respect to x is 2x, and finally we have equation number 3. Now start with equation number 2 again. Differentiate with respect to y. We have q equal to x plus f dash u, derivative of u with respect to y, and derivative of u with respect to y is 2y. So finally we have equation number 4. Now recall equation number 3 and 4. In these two equations we have x, y, p and q, and there is one more term, that is f dash u. So using equation number 3 and 4, we can eliminate f dash u. So from equation number 3 we have p minus y, this is equal to f dash u into 2x, and from equation number 4 we have q minus x, this is equal to f dash u to y. Now just divide these two equations or find f dash from one equation and substitute in the other one. We have p minus y divided by q minus x, this is equal to x minus y. Now just simplify this. We have partial differential equation given in the box. Consider this problem now. Z equal to f of xy divided by z. Here f is function of xy over z. So we define a new variable u, which is equal to xy over z. So we can say that z is a function of u is for the function of xyz, and z is for the function of x and y. Right? So we have finally this diagram you can see on the slide. So we start with equation number 2 and differentiate 2 with respect to x. We have curly z over curly x, which is p. This is equal to f dash u, and then derivative of u with respect to x. Now to calculate this derivative of u with respect to x, we have to be extra careful. Reason being, u is function of x, y, z, and just remember that z is for the function of x and y. So the derivative of u with respect to x is y is constant because we are taking derivative with respect to x, so we can just separate y. And now derivative of x over z with respect to x. And now this is given by equation number 2. Here z is not independent. It is function of x and y both. Now we can start with equation number 2. Differentiate with respect to y. Derivative of z with respect to y, which is q, this is equal to f dash u, and derivative of u with respect to y. Now on the same lines as we discussed above, we treat x as constant, and the derivative of u with respect to y is this one, z minus yq divided by z square, that is equation number 3. So I am just rewriting equation number 2 and equation number 3 again. In these two equations, we have again x, y, p, q, z and f dash u. So using 2 and 3 only we can eliminate f dash u. Simplify this expression and finally we have px minus qy equal to 0, and this is the required partial differential equation. Consider z equal to f of x minus y. We define u as x minus y and we can rewrite this differential equation as z equal to f of u. Now start with the equation. Differentiate with respect to x. We have p equal to f dash u and derivative of u with respect to x. And using u, which is x minus y, derivative of u with respect to x will be 1. So finally we have p equal to f dash u, that is equation number 1. Now again we start with z equal to f of u. Differentiate with respect to y. We have q equal to f dash u, derivative of u with respect to y. And derivative of u with respect to y is minus 1. We have finally equation number 2. From equation number 1 and 2, we just add them and we can eliminate f dash u, and finally we have partial differential equation p plus q equal to 0. Now consider this equation. It is in the form of arbitrary function f with two arguments, x square plus y square plus z square, and second one is z square minus 2xy. So here we have again z is some function of x and y. We don't have the exact relation. Everything is in terms of arbitrary function f. So to solve this problem, we define two variables as u equal to x square plus y square plus z square, that is the first argument of your function. Call this one as star. Then define v as second argument, that is z square minus 2xy by double star. So I can rewrite the given arbitrary function equation as f of u equal to 0, that is equation number 1. Now finally equation number 1 can be written as f is a function of u and v. U and v are functions of x, y, z using star and double star, and z is for the function of x and y. And I can always say that y is function of y and x is function of x, identity functions, right? Now we start with equation number 1. Differentiate it with respect to x on both sides. We have left side as partial derivative of f with respect to x, this is equal to 0. Now to calculate left hand side, we have to use chain rule, that f is a function of u and v, and u and v, they are further functions of x and y. So we have derivative of f with respect to u, partial derivative of u with respect to x, plus partial derivative of f with respect to v, and partial derivative of v with respect to x. And now we have the formula for u and v given by star and double star. We can find out the values of these two derivatives. So derivative of u with respect to x is 2x plus 2z into p. That is the first bracket, right, in equation number 2. And similarly derivative of v with respect to x. Now while finding this derivative of u with respect to x and derivative of v with respect to x, just remember that z is not independent, it is function of x and y. So we have equation number 2. Now on the same lines we differentiate 1 with respect to y. We have derivative of f with respect to y is 0, and now we have partial derivative of u with respect to y and partial derivative of v with respect to y. Use the formula of u and v and put the values. right? So we have finally equation number 3, partial derivative of f with respect to u into 2y plus 2zq plus partial derivative of f with respect to v 2zq minus 2x equal to 0. Now see equation number 2 and 3 carefully. We have two unknowns here, right? Partial derivative of f with respect to u and partial derivative of f with respect to v, and we have to eliminate these two. We can rewrite equation number 2 and equation number 3. Just shift the terms with partial derivative of f with respect to v on right hand side. We have starting two equations on this slide. Now we can divide left hand sides and right hand sides respectively. Cross multiply the expression, simplify this, and finally we have the partial differential equation given at the end in the box. Alright, here I am saying that divide equation number 2 and equation number 3. When we divide by any two numbers, then we are sure that these two numbers are not 0. So here I am assuming that partial derivative of f with respect to u and partial derivative of f with respect to v, right? At least one of them is going to be non-zero, because if both are 0, it means f is independent of u and f is independent of v. It means f is just a constant function, but it is not so, right? It is something like a system of equations, right? In previous example, while eliminating partial derivative of f with respect to u and partial derivative with respect to v, I said it is something similar to system of equations ax equal to 0. This is a homogeneous system of equations. It is always feasible. It has two types of solution. X equal to 0, that is trivial solution. We have this solution when determinant of matrix A is non-zero. It means its inverse exists. And we have a non-zero solution when determinant of A is 0. So in previous example, we were having two equations with x, y, p, q, z, and partial derivative of f with respect to u and with respect to v. So we can write down the coefficients of f of u and f of v in the form of matrix A, and we can take variable x as f of u comma f of v, right? And I said that at least one of them, f of u and f of v, is non-zero, right? It means non-zero because if both are 0, then f will be a constant function and we don't have any surface. So here f of u and f of v, at least one of them is non-zero. So if we talk about this homogeneous system, we can represent equation number 2 and 3 in the previous example as this homogeneous system, and we are saying that it has a non-zero solution. And if it has a non-zero solution, then the determinant of A will be 0. So whatever we did in the numerical problem, that thing is exactly same as saying that the determinant of matrix A is 0. So equation number 2 and 3 in the previous example can be rewritten in this form. See this expression carefully. Here capital X is our variable, that is partial derivative of f with respect to u and derivative of f with respect to v, and all other terms, this 2x plus 2zp and all other three terms, they are the matrix A. So we can write down equation number 2 and 3 as Ax equal to 0. And I told you that f of u and f of v both can't be 0 at the same time, otherwise function will be just 0 and we don't have any surface. So for a non-zero solution, determinant of A is 0, and if we put determinant A equal to 0, we have the same result as the partial differential equation for this particular problem. Consider example 5, z equal to x square f of y plus y square g of x, given by equation number 1. There are two arbitrary functions. One is f, another one is g. So the order of the partial differential equation will be 2. So we start with equation number 1. Differentiate with respect to x. We have equation number 2, which is p equal to 2x f of y plus y square g dash x. Start with equation number 1 again. Differentiate with respect to y. We have q equal to x square f dash y plus 2y gx, given by equation number 3. Now differentiate equation number 2 with respect to x. Now we have partial derivative of z with respect to x, second order, and equation number 4. Start with equation number 3. Again differentiate with respect to y. We have second order derivative of z with respect to y, and we have equation number 5. Now start with equation number 2, that is derivative of z with respect to x. Now differentiate this with respect to y. Now we have second order derivative of z with respect to x and y, given by equation number 6. We know that order of the partial differential equation will be 2, but we don't know the exact one. It will be in terms of second order derivative with respect to x or with respect to y, or it is mix of x and y. So we have to find out all the second order derivatives given by equation number 4, 5 and 6. Now we have 6 equations, and using these 6 equations we have to eliminate this function f, g, f dash, g dash, so that we have equation free from all these functions. So multiply equation number 2 by x and equation number 3 by y and add these two. We have following expression. The first one, left side is px plus qy equal to. If you see the expression on the right hand side, we can simplify this. We can collect few terms like x square f of y plus the last term y square qx, plus from the remaining two terms we can take xy common, and we have x times f dash y plus y times g dash x. So on the right hand side, the first expression in the bracket, we will use equation number 1, and for the second expression we use equation number 6. So first expression is z by equation number 1, and using equation number 6 this expression will be s by 2, and finally we have a partial differential equation and there is no arbitrary function f or g. Consider example 6, given by equation number 1, z equal to f of x plus ay plus g of x minus ay. Here if you want, you can define two new variables, u as x plus ay and v as x minus ay, that is arguments of these two functions f and g, and then you can take the derivatives. but here we have just one argument, so I am keeping this as it is. So start with equation number 1, differentiate with respect to x. Left hand side will be b f dash x plus ay plus g dash x minus ay, equation number 2, right? Now differentiate 1 with respect to y. We get q equal to f dash x plus ay. Then derivative of this argument x plus ay, it will be just a, plus g dash x minus ay. Derivative of x minus ay with respect to y will be minus a. So we have equation number 3. Now we find out r, that is second order derivative of z with respect to x. So it will be f double dash x plus ay plus g double dash x minus ay, that is equation number 4. Now we start with equation number 3. And now we differentiate with respect to y. We have now equation number 5. Not just using equation number 4 and 5, we can eliminate these two functions f and g, and we get the equation a square r equal to t. So this is the final solution. Try these numerical problems and formulate the partial differential equation. I have written solution of all these problems so that you can cross-check your calculations. If you have any doubt, then you can write in the comment section. Thank you.